Okay, so for today, I will start the class with discussion on the offline class. Okay, so starting from next week, most of our classes will be offline. So if you take a look at the schedule, okay, including today, we still have 4 more classes. So today, 14th of April. Then next week we have 21 and 22 April. And the week after, we have 28 April. When I check again, unfortunately for us, 29 April is cuti bersama. Okay, so we will consider this as a public holiday, so there will be no class on 29 April. So we only left with these 4 classes. So today, next week, we have 2 classes, and the week after we have 1 class. Okay, and in order to ensure that you can catch up well with the topics that I have delivered up until now for the preparation of the final exam. Okay, starting from next week, our class, we will do our class offline mostly. Okay, so 21, 22, 28, we will do our class offline. Okay, but for those who stick, who are sick and for because of unfortunate circumstances, you got COVID or something like that. Okay, in order to ensure that those students still can listen to my class directly, yeah, I will I will make it so the online is available as well. So actually, these 3 classes will be hybrid. Okay, but okay, I encourage you guys to come to the class offline. Okay, to come to the class directly, so I can teach you face to face directly on these 3 days. Okay, and I have already booked the room. So the room for this hybrid class will be for 104. So this room is actually in our faculty building, level 4. Okay, so please come to the class on these 3 days. Okay, for those who are sick or for those who are unfortunately got COVID like that, yes, you can still uh, join the class online. Okay, but for those who are uh, not sick, okay, if you are healthy, I ask you to come to the class. Okay, any question about the our class next week, starting from next week on these 3 days? Any question?
Sir,
Yes,
is there any specific things we should bring to the class?
not necessarily, just bring yourself and dress properly. Don't just use underwear like that. It's supposed to be enough. Okay, and just bring your notes. Okay, and then your own pen like that. I think that's supposed to be enough. Yeah. Nothing necessary for this. So there is no need to prepare something special. If you want to bring your calculator to practice as well, it's supposed to be okay. Yeah. And one more thing, I need to academic. I need to inform you as well, okay? Because you need to know about your schedule, about our final exam. Okay, our final exam, it will be held on the third week of the exam, so it will be on the last week of the exam. It's on the May 25th. Okay, May 25 from 12:30 to 15:30. Okay, actually, this schedule is there in your academic.idb.ac.id. So this is the schedule for your final exam, and based on the discussion in the class, based on the discussion between the lecturer, we will stick with this schedule. Okay, we will stick with the schedule. Okay, maybe some of you are wondering why suddenly we do this offline or hybrid class. It's most likely because statics, okay, is one of the subjects that need deep understanding. Okay, and to deliver the class full online, it will be hard for me to deliver all the things to you guys. Okay, sometimes there is a connection problem, and I cannot see your face directly. I cannot see your eyes directly, whether you understand or not about this. Okay, so at least I will use the last 2 weeks of our class for this offline meeting, mostly offline meeting. Okay, any question about this? So starting from next week, on Thursday at 10 a.m., instead of coming to the Zoom meeting like this, what you have to do is go to campus, go to FME building, our faculty building, and go up to the 4th floor and try to find this particular room. Okay, we will start the class at 10 in the morning, and the challenging one will be this one. Okay, Friday 22 April. Why it's challenging? Because the class will start at 7 in the morning. Okay, I will try to do this as well in order for you to get used to next semester, or maybe for some of you taking a short semesters, you have to get used to it, because starting from our short semesters, based on the information that I got, okay, most likely it will be full offline. Okay, starting from the short semester, and next semester as well, most likely it will be full offline. So like it or not, you have to come to campus. Like it or not, you have to attend the class, like that. And most likely in this period, in the short semester and the semester after, most likely we will not have this option anymore. So it will be full offline. Okay, so try to get used to it from now. And besides that, I need to meet you guys to see your understanding on our last several topics, to ensure that you can perform well in the final exam. Okay, any question about this? No, no question. Okay, so starting from next week, instead of meeting in the Zoom class, in the Zoom, we will meet at 4104, and the classroom for both Thursday class and Friday class will be the same. It will be at 4104, FME building level 4. Okay, I think if there is no question here, I will continue our discussion with the new topics.
I'm sorry, sir.
Yes, right.
My ticket going back to my home is at 21 April, and I have already bought it since last month.
In that case, okay, because the discussion is quite sudden for this one, I think I will still allow you to come to the hybrid class. Okay, but for the rest, okay, for those who hasn't bought the ticket yet, okay, try your best to come to the class. Okay, hybrid class is actually the online class. The hybrid, okay, is actually just for those who are sick. Okay, for those who are still going well like that, healthy like that, I prefer you guys to come to the class. Okay, because it's for your own benefit. Giving an offline, understanding an offline class will be much easier than understanding an online class. Okay, any other question? Nope. In that case, I think I will start our discussion on the maybe this is our last topic. Okay, the last topic of this semester is about friction. Although this topic actually consists of several parts. Okay, the first part it will be drive friction. Okay, in the drive friction there, I will discuss about the impending motion and the what you call that, tipping problem as well. Okay. Tipping problem. Okay. So this one is the basic of a friction, drive friction. Then after drive friction, we will discuss about wedges. Okay. For those who are wondering what is wedges, it's not the shoes that you like to use for those for a female student in this class, but wedges that what we want to discuss here is in bahasa we call it as a baji. Itu apa ya? Something like this. The shape is something like this. So some things that you use to stop the door from moving, something like that. Okay, those kind of wedges. Okay, that is our second friction topic, and the last one. But I'm not sure whether we will be able to reach this or not. Is power screw. Okay, most likely these two topics will be covered in our exam. These two topics will be covered in the last 2 weeks, but I'm not sure about this. Okay, if it's possible, then I will discuss about power screw, but if it's not, then we will just concentrate on the wedges. Okay, so those are the topics, the friction topics that we will talk about. And why it is important to discuss friction? Because in our statics problem, in our mechanics of materials problem, there are several times it is quite often that we face a friction case, a case with friction. So like it or not, we have to know about this. Okay, and I think we will start the discussion for today. Our main concentration is on this drive friction. Okay, maybe next week on Friday, we will start the discussion on the wedges. Okay, on Thursday next week, I believe I will still continue the discussion on this. As usual, after today's class, it's better for you to check for the EduNext for the homework on the drive friction. Okay, because our Friday class is gone because of holiday. the homework that I give it to you guys is more than usual. So I give 4 problems in our homework. Sorry, 5 problems. 5 problems in our homework. Okay, about dry friction. So try to check your EduNext, okay, by the end of the class or by this afternoon. And there will be 5 number of homeworks for the dry friction, and try to solve it. If you have a problem in solving the homework, next week on Thursday, we will discuss about it. Okay. And next week on Friday, we will start discussing about wedges. Okay. I'm not sure whether we will be able to reach for the power screw or not, but for sure, we can finish it until wedges. Okay. So when we talk about friction, let's talk about friction. Okay. When we talk about friction, there are several types of friction. Okay. The first thing that we will talk about is dry friction. Dry friction is friction which not involves any liquid. Okay. Dry friction is a friction which not involve any liquids. For example, dry friction which is happening on the surface between the asphalt and the tire of the car, like this. We call it as dry friction because there is no liquid there. Okay. Then the second type of friction is fluid friction. Fluid friction is friction which involves any liquid. Okay, for example, when you swim, okay, when you swim forward, okay, there is a friction. There is a friction from the liquid. There is a friction from the water, okay, which prevent you to go faster. Okay, those are the example of fluid friction, and beside that, there are several other examples. If you take a look at the engine of a car like that, most likely most of the engine in the car or in the motorcycle like that, we need to put oil in that. Okay, and when it runs, right, there is a friction as well between those moving parts, and because there is a oil there, the friction which is happening on those engine most of the time will be fluid friction. Okay, because it involves liquid. So that's the second type of friction. And when we add liquid like that in the dry friction, basically when we talk about the friction in the engine like that, it's actually a combination between these two. It involves liquid, but at the same time, okay, it also involves the moving parts as well. But the liquid there in this case is oil. The use of it is to reduce the friction between solid parts. Okay, so it's kind of combination between these two. Okay, when we talk about a fluid friction only is something like this. Or when you talk about airplane as well, it's fluid friction because air has its own fluidity as well. Okay, the last type of friction is internal friction. Okay, internal friction, we normally see it in the soil like that, like this. Okay, when we take a look at the soil or any kind of solid part, right? They normally have an internal friction. Okay, if you take a look at this, it's a picture of a landslide. Okay, the aftermath of the landslide. So you can see there, the things that is happening here is the internal friction there fail. Okay, so the internal friction there, the force which is happening there is bigger than the internal friction. So it landslides happen. Okay, but for you guys, okay, in our statics problem, because we are discussing about statics here, most of the time, the things that we will discuss about is only this dry friction. Okay, we will not discuss about this. We will not discuss about this. Yep. Okay, and I believe you have learned about friction as well from your high school year, and I believe as well in the first semesters when you take physics, right? You learn about friction as well. Okay. Alberto Hans, is it correct? You learn about friction in the first year in ITB?
Mu kinetic, mu static.
Yep. The one you did learn.
Yeah.
About it, right? Yeah.
Yeah.
So in the first year, when you talk about in physics problem, I believe you have discussed about friction as well. So the things that we will discuss today is a continuation of that. Okay. Let's us continue. Okay. Now we will talk about the dry friction, the detail on the dry friction. Okay, we will talk about the detail on the dry friction. In physics, right? When you have some kind of box like this, and then the box itself has its own weight, and then it has a contact with the ground, then there is a force P there, pulling force P, which try to move the box from one point to the other point. Okay. In physics, what you learned before, okay, this is the free body diagram that you normally draw. Okay, you have W, weight, and you have P, the pulling force, and then because there is a reaction between the ground and the box there will be normal force. Okay, and then because there is a friction in this surface between the box and the ground, okay, there will be friction force. Okay, when we talk about the free body diagram of the things that you learn in physics, most likely it's like this. Okay, and when the force P here is bigger than the friction force, it means that the things will move forward. Okay, but if the force P here is less than the maximum static friction force, okay, static friction force, then the things will stay stationary, something like that. Okay, and what you learned before as well, the friction force here, it depends actually. If it's stationary, then the friction force here is supposed to be equal to the normal force multiplied by mu s, where mu s here is the static friction coefficient. Okay, but if it is moving, if the things here happens when it's moving, okay, like it or not, instead of using friction force, which is equal to normal force multiplied by mu s, okay, the static friction force, if it's moving, okay, we will have to use this kinetic friction force. It is normal force multiplied by mu, sorry, not mu s, it's supposed to be mu k. Okay, where mu k here is a kinetic friction coefficient. And based on what you learn, okay, based on what you learn in the physics, right? Normally, mu k is supposed to be less than mu s. Okay, mu k is supposed to be less than mu s. So because of that as well, the friction force, the kinetic friction force, is normally smaller than the static friction force. Okay, that's what you learn in physics and what you learn in your high school year as well. So the things that I talk about here is actually a review of what you have learned before. Okay, but if we want to take a look in detail, okay, if we want to take a look in detail, and we have to take a look in detail in our statics discussion for the friction here. Okay, this is what is actually happening. So instead of like this, okay, the thing is that is actually happening is like this, and it is logical. Why it is logical? Because when we take a look at here, when we take a look at the normal force, when we take a look at the friction force, okay, it's supposed to be happening at an area, the contact area, and the contact area is supposed to be the one at the bottom here. So the normal force and the friction force, instead of both of it as a concentrated force, the most correct way to represent it is to represent it as a distributed force like this. Okay, distributed force. So it's supposed to be distributed along the area, the bottom area here. Okay, for both friction force and normal force. And if we take a look in detail, okay, if we take a look in detail, this part, okay, if we zoom in at those part, actually the real thing that is happening at the contact surface is supposed to be like this. Okay, so there's supposed to be a normal force there at each contact point, because later in your second or third year, you will learn that nothing in this world is completely smooth. So when we take a look at one thing and it looks smooth, but if we zoom in microscopic level, most likely those things it won't be smooth, completely smooth. So it must be certain roughness there, and those roughness will affect the friction which is happening at those two things. Okay, the roughness of the first thing, the box, and the roughness of the ground as well, it will affect the friction force, because what is actually happening in the contact area between those two is actually like this. Okay, because there is a roughness of the box and there is a roughness of the ground surface. Okay, the contact will not be happening at the whole surface, but the contact will be happening at certain point where it is slightly protruded among the others. So the contact, this is the contact point that is supposed to be happening, and at each contact point there will be normal force and friction force. Okay, so this is the things that is actually happening when we take a look at things which have a normal force, which has a friction there. Okay, but you don't have to worry about it. Later, as what we discussed before in the distributed force, okay, we can represent this kind of a distributed force, okay, like in the normal force or in the friction force, as a concentrated force. But because of this as well, okay, not necessarily everything will happen at the center. So previously, when you talk about friction, when you learn about friction, okay, you see that the normal force is always happening at the same line as the weight. Okay, it is not necessarily it won't be always the case here. Why it won't be always the case? Because normal force is actually the normal force that we have here is actually a representation of the distributed normal force here, and not necessarily it's constant on the surface. It can be linear. Most likely it will be it is linear. So not necessarily the normal force will be exactly on the same line as the weight. It can be here, it can be here, depend on the condition. Okay, that's the thing that I want you to understand at the beginning about the basics of it. So later, you know why the normal force that we discuss about can be in the location where it is not in the same line of action as the weight. Okay. Up until this point, is there any question?
Sir, just want to make sure that the third picture at the bottom is just the zoomed version of the distributive force, right?
Yes,
The close-up shot.
correct. This
Okay,
one, right? This one is actually the zoom version of this. So
okay.
if we zoom in a little bit at this location, for example, this is what will be happening there. Okay. Okay. Any other question? Any other question before I try to continue with our discussion? If not, then I will discuss more about this dry friction, and later at the end of the class I will discuss about some problem example. This is the continuation of what we discussed before, okay? Because the friction force is like this, and the distributed friction force is like that, and the distributed normal force is like this, okay? That's why when we take a look at it, okay, in some condition, this kind of thing is possible, where the concentrated force, which is representing the distributed normal force, will not be at the same line of action as the W here. Okay, so this is the difference that we will talk about quite a lot of time in comparison to the things that you have learned in physics. This is the things that you have learned in physics, okay? And in our case, most of the time we will discuss it like this, okay? So basically, if we want to differentiate between these two discussions, in physics, we assume all the things there as a point. So although you have a box, okay, we assume this box as just one point, which has no length, which has no width, like that, okay? But in our statics discussion, okay, when we talk about a box like this, okay, we consider the dimension of the box. We consider the dimension of the box. So we will not see this box as a point. Okay, we will see this box as a box which has length, width, depth, like that. Okay, that's why as well, because it has length, okay, the normal force, the friction force, will be distributed on the contact surface. Okay, will be distributed on the contact surface, and because the normal force it won't be linear, so it won't be constant, it will be linear most of the time. Okay, the concentrated normal force, which representing the distributed normal force, most of the time will not be the same at the same location as the weight. Okay, something like that. Okay, so this is one of the case where we know the weight, we know the force P. Then when we take a look at the normal force, okay, the normal force which is happening there is not exactly on the same line of action as the W, and there is a friction force here. Okay, why it's always like that? Because when we take a look at this, okay, you can see that there is a P here, pulling force P there, and there is a friction force F there, which is the concentrated force form of the distributed friction force. Okay, when you take a look at these two, okay, because equilibrium in the x direction, the friction force will be the same as the pulling force P there. Okay, when statics happen, and there is h here, the distance between those two. Okay, when we take a look at that, we can see that P and F here is a couple. Okay, and it will create a clockwise moment. And on the other hand, when we take a look at the W and the normal force here, when we use a sigma Fy equal to 0, okay, normal force here will be the same value as the W, but at the same time as well, there is a distance x there between those two. Okay, and if you take a look at that as well, these two will create a couple, and those couple will create a counterclockwise moment. So basically, in order to ensure that the statics equilibrium happening, okay, because the pulling force there is at the middle of in the middle of the box, okay, and the friction force is at the bottom of the box, okay, and there is a distance there, vertical distance between those two forces. There will be a couple, clockwise couple, and because of this as well, we have W and we have N, which is equal to W. Okay, and there must be distance here as well. Why there must be distance here? Because this moment need to nullify this moment. So in order to cancel out the moment which is happening because of this, okay, this one, there is we need to have a moment because of weight and normal force. That's the thing. Okay, that's the thing. Because if not, if you just force it, if you just force normal force, okay, to have exactly the same line of action as W, okay, there will be no moment there. And if it's the case, then the moment which is available in this free body diagram will be just from this. And in that case, instead of staying stationary, okay, the box will rotate clockwise, which is not happening. Okay, so like it or not, the normal force there must the normal force and the weight there must give a moment, counterclockwise moment, to nullify the moment due to the pulling force and the friction force. Okay. Until this concept, anyone want to ask question? So for example, maybe I will give a value. For example, if our W here is 10 Newton, okay, and our pulling force here is just 2 Newton, okay, and the static friction coefficient mu s is 0.5, okay, using sigma Fy equal to 0, in this case we will get that the normal force is equal to 10 Newton. Using sigma Fx equal to 0, we will get that the friction force is equal to 2 Newton. Okay, and you can see that there is height here. The height of the pulling force, for example, I will put it as 10 millimeter. Okay, so because of pulling force and the friction force, there will be clockwise moment 20 Newton millimeter. Okay, that's why if we use sigma moment, for example, at the O here equal to 0, what we will have later, it will be P multiplied by H. Okay, minus W multiplied by X equal to 0. Okay, so you can see that P is 2 Newton. Yeah. Okay, we can see that P is 2 Newton. Newton multiplied by H there is 10 millimeter minus W, in this case 10 Newton, multiplied by X equal to 0. In this case, we will get that the 20 is equal to 10X. So X is equal to 2 millimeter. Like that. This is some of the case that maybe some of the problem that maybe you have to face in the future. Okay, so this is one of the example there. Okay, and the X here, okay, the X here is actually showing you as well that if the X is too big, okay, there will be a tipping effect. Okay, so for example, yeah, in this case, okay, in this case we have the height there, sorry. Later I will discuss about it, quick tipping effect. But when we take a look at this, okay, X here can only be from, so the location of the normal force, it can be from this point until this point only. Okay, it can be anywhere between those two, but it cannot be outside of the surface. Okay, it cannot be outside of the surface. Maximum is only on the edge, only on the edge. Maximum is it only can be on the edge only. So it cannot be outside here, it cannot be outside here. Okay, in between those two edges, yes, it is possible. So this is the location where normal force location is possible. Okay, tipping will happen. Tipping is like this. For example, if you have a box like this, wait. Yeah. If you have box like this, then you push the box, and this is the ground like that. And if tipping happen, this is the things that will happen. Instead of the box sliding, okay, instead of the box sliding like this, okay, try to take a look at my video, okay. Instead of the box sliding like this, when we talk about tipping, this is what happening. Okay. Yeah, it will rotate. Okay, it will roll over. Okay, so that what we call as tipping, and tipping will happen if the moment equilibrium is not fulfilled, cannot be fulfilled. If the moment equilibrium cannot be fulfilled, then tipping will happen. Okay, to discuss about tipping, I think I will use the session, next week session, to discuss about tipping. Okay, for today, I think I will just concentrate on the impending motion and all the translational all the translational things. Okay, about tipping we will discuss it next week, but it is there. So the location of the normal force, it will affect the behavior of the holdings. Okay, so it can be just stay stationary, it can be just sliding, it can be tip over as well. Okay, but before we go for the tipping things, okay, we will concentrate on this. Okay, static and kinetic friction, and we will concentrate on the types of friction problem. These three types of friction problem when the impending motion exists. Okay, or this one. So this is the case that we normally face in the real world. Okay, this is the things that we will discuss today mainly. And this one is mostly translational friction. So it's mostly translational. We don't talk about the rotational. We don't talk about the tipping yet. Okay, but before we go there, okay, when we talk about the normal force, friction force, like that, okay, when we talk about friction force, as I told you before, there are two types of friction force. Okay, the static friction force and the kinetic friction force. What are the difference between those two? Okay, when we take a look at this, okay, the free body diagram is as you can see here. So there will be pulling force like this, W like this, then normal force like this, then friction force like this. Okay, try to imagine if the pulling force is very small. For example, in this case, our W is like the previous case. Okay, our W is 10 Newton. Normal force is 10 Newton because sigma Fi equal to 0. The pulling force is only 2 Newton. Okay, the friction force, sorry, the mu s here is 0.5. Okay, let me charge my laptop first. Yep. Okay. For example, in this case, mu s is 0.5, and mu k is slightly lower than that, 0.3, for example. Okay. In this case, if we calculate for the maximum friction force is supposed to be the same as the static friction force. Okay, it's supposed to be, sorry, it's not the static friction force. The maximum friction force, F max. Yeah, what is happening? Okay, it's supposed to be the same as normal force multiplied by mu s. In this case, okay, the maximum friction force is 10 Newton multiplied by 0.5. In this case, 5 Newton. That's the maximum friction force. Okay, and we can see here that the in this case, the pulling force P, 2 Newton, is still under the maximum friction force, 5 Newton. So in this case, the condition is still in this stage. Okay, so the friction force here, it will be the same as the pulling force. What happened here? Something like that. Okay, so that is the first condition. Okay, the first condition is no motion. Okay, the first condition is no motion. In this case, it means that the horizontal, the force in the same direction as the friction force is smaller. So in this case, P is smaller than the maximum friction force. Now what is happening here? What the... Wait a minute. Okay, so the in this case, the first condition is static friction or no motion. Okay, the P is smaller, the pulling force is smaller than the maximum friction force, F max. So this is, for example, the first condition. Okay, now the second condition. The second condition, okay, where the moving is happening, kinetic friction is happening. Okay, the second condition is where the kinetic friction happening. The kinetic friction happening is when the P, okay, pulling force is slightly more. It is more than the maximum friction force. What is happening here? Okay, maximum friction force. Okay, sorry for the writing here. I don't know why. What is happening with this? That's the second condition. So this is the first condition, and this is the second condition. Okay, when the second condition happen, yeah, when the second condition happen, the real friction force which will happening, it will depend on the kinetic friction force. Okay, it will depend on the kinetic friction force. Okay, for example, okay, if the weight there is 10 Newton, then the P there is, for example, instead of 2 Newton, it will be 6 Newton. Okay, as you can see here, F max, if we calculate, is 5 Newton. So you can see that the P is bigger than the F max. So P is 6 Newton. F max is 5 Newton. Okay, and because of that, we know that it will move forward. Okay, we know that the box will move forward. Okay, because we know that the box is moving, Then instead of using mu s, we will use mu k for the next calculation, okay, for the friction calculation. So the friction which is happening here, okay, will be F equal to 0.3 multiplied by the normal force, because the mu k is 0.3 multiplied by 10 Newton. So in this case, the friction force will be 3 Newton. And then you can see there that there is a difference in the horizontal force from the P and the friction force. And that difference will be used to accelerate this mass here. Okay, that's the second condition. When motion happens, second condition is motion happen. The first condition is static friction, no motion. Okay. The third one is impending motion. When we talk about impending motion, we talk about this specific location. Okay. So what is actually happening here? This is the example. Okay. When P is equal to 5 Newton, okay, when P is equal to 5 Newton, then we take a look at the F max here, the maximum friction force due to the maximum static friction force. If we calculate, the maximum static friction force is 5 Newton. As you can see here, P is equal to the maximum friction force. So impending motion here is condition where P is equal to the maximum friction force. Okay, so here what is actually happening, the friction force that really happening is 5 Newton, the same as the F max. Okay, and it's still not moving, but it's about to move. That's the definition of impending motion. Okay, and if we take a look at the value of the friction force in comparison to the P value, the pulling force, you can see there that at the first condition, okay, at the first condition, this one, okay, this is the line of the first condition. So when P is small, for example, P is 1 Newton, the friction force will be 1 Newton. P is equal to 2 Newton, it will be 2 Newton. 3, 4, until it reaches the third condition, impending motion. In this case, is 5 Newton. P is equal to the F max, mu s multiplied by n. Okay, that's the maximum that the friction force can give. That's the maximum pulling force before motion start to happen. We call that as impending motion. Motion about to start, like that. Okay. Beyond that, above that, if P is bigger than F max, okay, if P is bigger than F max, okay, this is the things that will be happening. Okay, this is the things that will be happening. But in this case, normally, in our case, normally, we will assume that this one is a constant line. Constant line like this. So when motion start to happen, okay, we will use mu k instead of mu s. Okay, and when the motion start to happen, when the P, the pulling force, is bigger than the maximum friction force. You can see, right? P here is bigger than the maximum friction force. The maximum friction force here. Okay, because the P is bigger than maximum friction force, the friction force cannot hold it anymore because it reached the maximum and it cannot go beyond that. Okay, and because of that, okay, motion starts to happen, and because motion starts to happen, okay, we have to use mu k instead of mu s. That's why the friction force that is happening there, instead of mu s multiplied by n, is mu k multiplied by n. In this case, is 0.3 multiplied by n, so 3 Newton. That's the second condition. Okay, about these three conditions, anyone here want to ask question? Anyone? No? No question here?
Sir, can I ask?
Yep. Of course.
Just to make sure, so the first condition is the no motion, second condition is motion, and the third condition is impending motion.
Yes.
So it's actually still no motion.
Yeah, number 3 is actually no motion, but the motion starts about to happen. If
Okay.
the force is slightly more, if we increase the force slightly more, then it will move like that. Okay. But
So the third
it's not
condition is
general.
between first and second, right?
Sorry,
So third condition is between the first and second condition.
that condition is in between the first and the second condition. Yes.
Okay, thank you, sir.
So this one is the first condition, this one is the second condition, and this one is the third condition. Okay. So in that case, I will continue. Beside that, okay, beside friction coefficient and the things that you have learned before, okay, in this statics problem, we will introduce you with new terms here. Okay. Vs and Vk. Okay, Vs and Vk. What is Vs? What is Vk? Vs is the angle between the resultant between the friction force and the static friction force and the normal force. Okay. It's you can see right here we have a static friction force, we have a normal force. Okay, and if we make a resultant of it, the angle between the resultant and the normal force, it will be Vs. On the other hand, okay, if there is a motion, okay, if there is a motion instead of impending motion, okay, we will have a kinetic friction force. Okay, and normal force, the resultant between both will be the RK here, and the angle between the RK and the normal force, it will be Vk. Okay, so the angle here is actually just to represent the condition of impending motion and the condition of motion. So in the condition of impending motion, yeah, our third condition, in the condition of the impending motion, the Vs here, okay, is actually, you can see that it's a arcus tangent of Fs, this one is Fs, right? Arcus tangent of Fs divided by n. Yeah, so Vs is the arcus tangent of Fs divided by n. Okay, and Fs there, because it's depending motion, is equal to mu s multiplied by n. Equal to mu s multiplied by n. That's why if we take a look at this, okay, Vs is supposed to be the same as arcus tangent of mu s. That's the condition of impending motion. Okay, then the second condition, the second angle is Vk. Vk here is the angle between the normal force and the resultant k in the motion condition. Okay, Vs is the angle between the normal force and the Rs in the impending motion condition. Okay, for the motion condition is Vk, is the normal force, the angle between normal force and Rk. Okay, and if you take a look at that, it's supposed to be the Archies tangent between the Fk and the normal force. Okay, like this. So, and if we take a look at Fk, Fk is supposed to be mu k multiplied by n, right? And we can simplify it, this one and this one. So, Vk here is supposed to be the Archies tangent of mu k. Okay. The usage of this is sometimes we don't use it quite often, but sometimes we use it. So it is better for you to know about it. Okay, the angle Vk, the angle Vk and the angle Vs. Vs is the angle between resultant and normal force in the impending motion condition. Vk is the angle between resultant and normal force in the motion condition. Okay, then I want to talk about things that is very important for us. Okay, when you face a friction problem later, okay, when you face friction problem later, normally we can differentiate the problem into three conditions. Okay, three conditions there is different between one and the other. The way to solve it is different between one and the other. Okay, the first condition is the condition where in the problem we know that the impending motion is known to exist. So for example, in the problem, it's stated there that in this problem, the impending motion is happening. So that's the first type of problem. When we know that impending motion is exists. Okay. Then I will go to the third one first because this one is the easier one. I will talk about the easier problem first. Okay, when we know the relative motion, so motion is exists. Okay, so if we know that there is a relative motion between the contacting surfaces, then it is we can consider it as a third types of problem. Okay, the first problem and the third problem is quite simple. Why? Because in the first problem we can just use mu s. In the third problem we can just use mu k directly for the friction force. The friction force here, it will be friction force kinetic. The friction force here will be friction force static. And if it's impending motion, the condition is known to be impending motion, it's even easier. The friction force there is supposed to be F max. Okay, the first and the third problem is easy. The harder one is supposed to be the second one. Okay, we don't know yet whether it's impending motion condition or motion condition. So we don't know whether the things will move, or we don't know yet that the things will stay stationary. That's the second problem. And most of the problem actually is the second problem, which is the most difficult one. Okay, but you don't have to worry about that. The solution is there, so we can still solve it. Okay. In order for you to get used to it, I think I will just show you guys some of the problem example. Okay, this is the first problem example. Okay, uniform crate has a mass of 20 kilogram uniform. If a force P 80 Newton is applied to the crate, determine if it remains in equilibrium. The coefficient of static friction is mu s equal to 0.3. So the problem here is just to check whether it stays stationary or not. Okay. William, hello William.
Yes, sir.
Where we supposed to start in this particular problem? What we supposed to do in this particular problem, William?
I think I would draw the free body diagram first.
Correct. Always start with the drawing free body diagram. Yeah. Okay, we will start with the free body diagram. Okay, for example, this is the freight. Then we have a force 80 Newton there, 30 degrees. And the height there is 2 meters. The length there is 0.8 meters. Sorry, 0.2 this one. 0.8 meter. Okay. What will we have here? What other things that we have here? If we use G equal to 10 meter per second square.
The weight is 200 newtons.
Okay, yes.
Downwards from the center of gravity. Yes.
Yeah. And why it's the center? Because it is stated there that it's uniform grade. Okay, so it must be at the center. 200 Newton, 20 kilogram multiplied by 10. Okay, 200 Newton. What else that we're supposed to have here?
The friction.
Friction. Okay. The friction where we're supposed to I think before we go for the friction, I think it's better for us to just add the normal force first. Okay. So we have a normal force. Wait a minute. So I think just put it here. This one is normal force. Then beside normal force, we will have friction force. Okay. Then what should we do here, William? In this case,
sigma just state that the distance between the and the normal force and the weight is a variable such as x.
Okay, you can do that. What else?
And then as sigma moment equals to 0.
Sigma moment equal to 0. I think we cannot go directly to sigma moment equal to 0. We're supposed to solve it one by one, right? In this case, if you want to use sigma moment equal to 0, sigma moment against which point?
Oh, sorry. Should it be check whether the P equals to F?
P equal to F. Yes, we can do it that way. But I think this one, okay, friction force is actually variable, which is very dependent on the normal force, right, William? So actually, it will be beneficial for us to know about the normal force first. Okay, so actually, it's supposed to be okay for you to solve for the friction force first. Just use sigma fx equal to 0 like that, right? And you can see that there is a horizontal component 80 Newton cos 30 degrees is supposed to be the equal to the friction force. Okay, and if we use sigma fy equal to 0, we will get that the 200 Newton plus 80 Newton sin 30 degrees minus n will be equal to 0. Correct, right, William?
Yes, sir.
Yeah. In this case, we will be able to find the normal force. So we will get that the normal force is equal to 200 Newton plus 80 Newton sin 30 degrees. What is the value of that?
600, sir.
Huh? Sorry, 600?
600. Sorry, it's 80, so it's 240.
240. Sin 30 degrees is what? Half.
Yes.
Yeah, okay. So 240 Newton. So we know the normal force. And now what we have to determine here is whether it's in equilibrium condition or not. Okay. So what we can do is we can compare, in this case right now, we can compare whether the F max, which is happening there, is in comparison with the F in the equilibrium condition is like what? Okay, so for example here, I will use sigma fx equal to 0 to find out in the equilibrium condition, what is the value of F? Yeah, in this case, in the horizontal condition, in the horizontal direction, I will only have 80 Newton cos 30 degrees minus F equal to 0. So in this case, our F will be 80 Newton cos 30 degrees. What is the value of that, William?
40 times the square root of 3.
In decimal?
Wait a second. Around 69.3, sir.
69.3 Newton. Yeah. So this is based on the equilibrium, friction force based on the equilibrium. Okay. Now take a look. We have to take a look again. The value of our F max is supposed to be the maximum friction force possible. Is this value is smaller or bigger than our F max? Okay, that's the thing that we have to check. As simple as that. Okay, our F max value is supposed to be like what, Liam?
Should be the normal force times the static friction coefficient.
Is 240 Newton multiplied by 0.3, right? What is the value here? Supposed to be 72, right?
Yes.
72 Newton. Now, would you mind to compare both? Which one is bigger, F max or F?
The F max is bigger.
F max is bigger. Okay. If you take a look at this graph, okay, the things which is happening in the current condition is which one? Is it in this region, impending motion region, or in the kinetic region?
In the static region.
In the static region. Why we can determine it like that? Because the friction force based on the equilibrium that we calculate is smaller than the maximum friction force. So in this case, the condition is stationary. Did you get it, William?
Yes, sir.
Yeah. If the friction force here is the same as our maximum friction force, okay, what condition that is happening there?
Impending motion.
Impending motion. In this case, is impending motion. The last one, which is not possible. Okay, based on your calculation, the F is bigger than the F max. Based on your calculation here, okay, using this free body diagram, the F is bigger than the F max. What is happening there actually?
It started to move.
Yeah, it's moving. Actually, this condition is actually showing us that it's moving, but because of that, because we know that this one is moving, okay, the free body diagram is actually wrong. Okay, and the calculation is actually wrong. So this one, it won't be, if it's moving, it won't be Fs or F anymore, but it's supposed to be Fk. And there will be a delta F horizontal, which will accelerate the rate horizontally. Do you get it, William?
Yes.
So this is the first problem example for this. Okay.
Sir, I want to ask,
Yes, yes.
how do you get the Fmax? Where there's the 0.7? Where's the 0.7?
Sorry, Rehan. I don't get you.
How do you get the Fmax?
This one. We know that mu-s is 0.3, right?
Yes.
So based on our discussion before, Fmax, okay, the maximum friction force available is always the normal force multiplied by the mu-s, right? Do you get it, right?
Yes.
Yeah.
Yes.
So in this case, in order to determine whether which condition which is exists in this particular problem, what I try to do is to compare the friction force. Okay, the friction force which is happening, which based on the calculation of the free body diagram here. Okay, I want to compare the friction force from the calculation of the free body diagram here with the Fmax. Okay, if the friction force based on the calculation is smaller than the Fmax, it means that the condition is still static, right, Reinhard? Because
Yes,
the friction is still smaller than the maximum friction force. Okay, but if it's the same, then it's supposed to be impending motion, right? Because
Yes.
the friction force is the same as the maximum friction force. Last one, if Fx, if F is a friction force is bigger than Fmax, in this case, it's supposed to be not possible, right? Right? Because the maximum friction force is only 72 Newton. And if the friction force is bigger than that, it's not possible, right?
Yes.
Yeah. In that case, it means that the pushing force, the 80 Newton pushing force is too much. The 80 Newton pushing force is too much, which means that the friction force cannot handle it anymore, which means that the crates start to move. The crate's moving. Okay, Reinhard?
Okay, so
That's the way to determine it. If the friction force is bigger than the maximum friction force, then it's supposed to be moving. And the free body diagram, the calculation is wrong, because here, if it start moving, then the friction force there is supposed to be Fk instead of Fs or instead of F. Do you get it, Reinhard?
okay, sir. So if the force is bigger, the force is bigger, then it is not equilibrium, right?
Yep, correct. Because if the F is bigger than Fmax, it's not possible, right? So in this case, that the friction force to hold the things in place is bigger than the Fmax, so it's not possible. So most likely the things is not in equilibrium, so it's in moving condition. Do you get it?
Okay, sir. Thank you.
And in order to draw the free body diagram correctly, we have to replace it with Fk, because we know that it's moving, right?
Yes, sir.
Okay, any other question about this? If not, then I will continue with the next one. Okay. You can see here that there is a dump truck. This is the dump truck, as this, and this is the dump part of the dump truck. Okay. When dumping the things, right? Dump truck normally start to tilt the ground here. Start to tilt the bucket there. Okay. Okay, by using the actuator here and here. And the question here is, in the condition of dumping here, okay, the bed of the dump truck, this one, is raised to an angle of 25 degrees, like this. This one, the angle is 25 degrees. Okay, the vending machine will begin to slide off the bed. This one, we are talking about the vending machine here. This one, if we take a look at the zoom in picture, Okay, the vending machine will begin to slide off the bed. Okay, begin. This is the keyword here. Begin to slide off the bed. Now, you are asked to determine the static friction coefficient between the vending machine and the surface of the truck bed. This one. Okay, you are asked to find out mu s, static friction coefficient mu s, between these two. So we know that at the angle of 25 degrees, okay, the vending machine start to slide. Okay, now, based on this particular problem, try to take a look carefully on this particular problem. If you want to give a comment on this, okay, among these three conditions, which condition is actually there, exists in that particular problem? Condition 1, impending motion is known to exist. Condition 2 is not yet sure about what condition is exists. Condition 3, relative motion is known to exist. Which one do you think is there, exists in this particular problem? Anyone can give a comment on this?
I think it's condition 1, impending motion.
Correct, William. It's impending motion because it starts to slide off the bed. So at the angle below 25 degrees, so if you can see here, the condition is from 0 degrees, then it starts increasing bit by bit until it reaches 25. When it reaches 20, before it reaches 25, it stays stationary. But when it reaches 25, it starts to move. So the condition here is actually the condition at the limit condition. So this is the limit condition. So we can say that this condition is impending motion condition. Because we have keyword here, begin to slide. So the starting point of the sliding. Okay, so that's the limit condition. Okay, anyone want to ask question about this? Why this condition is impending motion condition? If you are still confused about this, let me know and I will try to explain to you guys before I start discussing on how to solve this. Anyone? No? Okay. So based on our discussion just now, we agreed that this condition is impending motion condition. Okay, impending motion exists. Yeah, impending motion exists. Reinhard Rema, Reinhard, oh yeah, sorry, Reinhard, just now you already asked about it, but you haven't helped me to answer the problem, right? Okay, anyway, you're the class leader, right, Reinhard?
Yes, sir.
Okay. About this, what we're supposed to do first, Reinhard? After we know that impending motion is exists.
Draw the free body diagram.
Right. Always start with drawing the free body diagram. Okay, for example, that's the case. What we have here, what forces that we have here? Weight at G, right? So, but we don't know the value of weight yet, right? So we don't know the weight of this yet. So, but it's okay. We can just put the weight there. W. And the condition there, we know that here is 2.5 feet. And this one is 1.5 feet. This one is 1.5 feet. Okay, what else?
Friction force and normal force.
Friction force and normal force. Okay, friction force. I think I will just assume that it's Wait a minute. Normal force. Normal force is going which way?
Apa namanya?
Its normal force is always normal to the contact surface. So it's supposed to be going which way? Reinhard.
Tegak lurus sih. Tegak lurus sama
Perpendicular to the surface, okay?
perpendicular.
Okay. Perpendicular to the surface, so it's like this. So this one is normal force. Friction force is supposed to be supposed to be parallel to the surface, so it's supposed to be like this. This one is friction force. Okay, so those are the forces that we have here, and we know the condition is impending motion condition, right?
Yes.
Now, what we supposed to do after that? If we know there is impending motion, do we know the value of F in terms of N? Friction force in terms of N, do we know the value of friction force in terms of a normal force? If we know the condition is impending motion. Reinhard?
Yes. Sir.
Yeah. So friction force supposed to be normal force multiplied by what?
Static coefficient.
Yep.
Friction.
Yes, correct. So actually here, the friction force here, we can replace it with the N multiplied by mu S. So we have N, we have N multiplied by mu S, we have W. Okay, but now we have to solve for the mu S, right? What we supposed to do? Reinhard?
Using sigma fx and sigma fy.
Okay, we can try to use sigma f x equal to 0, and we can use sigma fy equal to 0. Okay, I think in order to ease the calculation, I will just use y is using this direction and x is using this direction. So y is perpendicular to the surface, contact surface, x is parallel to contact surface. Okay, if we use the sigma fx equal to 0, what we have there?
W sin 25.
W sin 25. Yes, correct. It's supposed to be sin. W wait sin 45. Sorry, sin 25. Sin 25 degrees.
Minus f.
Minus f, but our f is already
And
yes, right?
yes.
Equal to 0.
Equal
Then
to 0.
if you use sigma fy equal to 0, what we have?
W cos 25 minus W cos 25 plus N equal to 0.
Okay, plus N equal to 0. Actually, it's just the same. I can just use the minus of it, and this one is minus.
Okay.
Should be okay. And then what should we supposed to do here? In order to get mu s, what we supposed to do? Reinhard. We can substitute and eliminate, right?
Yeah, substitute.
Yeah. Using the second equation, n is equal to W cos 25
Yes.
degrees. So we can just substitute this to this value, right?
Yes, sir.
So if we substitute that into the first equation, what we will get is W sin 25 degrees minus
W cos
25 degrees multiplied by mu s equal to 0, right? In this case, if I rearrange term, what we get is W sin 25 degrees equal to W cos 25 degrees multiplied by mu s. So in this case, mu s will be equal to what? W
sin 25.
25 degrees divided by W cos 25 degrees. W we can cross it. So mu s here is supposed to be tangent, right?
Yes, sir.
Tangent 25 degrees. So that is our mu s. Okay, Reinhard?
Yes, sir.
You understand, Reinhard?
Yes, I understand.
Okay, good. I think we can practice one more here, but this one is tipping effect. Although later in your homework, there is one particular problem about tipping effect. Wait a minute, let me show you guys about our homework.
Sorry, sir. I have a question first for the previous sections.
Yes, but
I think that
sorry, who's this?
it's Shan, sir.
Oh, Shan.
Earlier, I think
Sorry,
you.
did you join the previous exam?
I did, sir.
Okay. Your condition currently supposed to be okay, right?
Oh, yes, it's okay.
What is your question?
Earlier, I think there's the equation for arcus tangent mu s, yes, sir. Before in the beginning of the class, I think.
You mean this
So
one?
so does that work on these kinds of these types of questions, sir? So, for example, we have an angle, we can just use tan of that angle to find the mu s.
Yes, actually, yes. We can use that. Okay. So basically, because this one, right? If the condition is a sorry, which one? This one. This one. The condition is impending, right, Chan?
Yes, sir.
If the condition is impending, you can see here that we can use this one. Rs is the resultant of Fs and N. Okay, and Vs is the angle between N and the Rs. Okay, so if we draw again about the free body diagram, like this, for example, there is a weight here, going like this, weight, okay, and there is a normal force, and there is a Fs, friction force. There. Something like this. Okay. And the resultant of both is supposed to be like this. For example, this is the result. And this one is the angle. Vs. Do you get it, right?
Yes, sir.
The resultant in this kind of action, the resultant is supposed to be the same line of action as the W shape. Why it's like that? Because the condition is, although it's impending motion, but all the things are what you call this? All the things are in equilibrium condition, right?
Yes, sir.
So if in the equilibrium equation is supposed to be happening, Rs is supposed to be at the same line of action as W. That's why the result there for mu s is the same as the tangent 25 there. It's because of that, because Rs there is supposed to be in the same line of action as W. Do you get it? But if you solve it this way, this one is the line of action of RS, this one is the line of action of W. It's supposed to be in the same line of action in order for us to have an equilibrium condition. Do you get it?
Yes, sir.
So the result is the same. That is why the result is the same. Okay. Vx then is supposed to be same as 25 degrees. So mu s is supposed to be tangent 25 degrees. So that's the result is supposed to be the same. But if you do it that way, I'm afraid that we miss the process. That's why I didn't teach you to solve it that way. So what I try to inform you guys here on how to solving it is by solving it one by one using the equation that we have. You get it, Sam?
Okay, sir. Thank you, sir.
So this one is impending motion. So basically, wait a minute. If this is your homework, yeah. You can see, right? This is your homework later. Some of the problem, basic problem, but some of those are tilting problem. I think you can try to learn it by yourself first on the tilting problem. So basically, when we talk about tilting problem, we can just move the force. But this one, the force is only concentrated on this point. Next week we will discuss about it, but try to do it first so you can try to learn by yourself about the tilting problem and some other problem example as well here. Try to finish it by yourself in your homework. The homework, I will publish it maybe in the afternoon. Okay, my assistant will post it there, but you can check later. Okay, wait a minute. Yeah. So basically, this is the tipping effect. Okay, later this one will be part of your homework as well, but I will discuss a little bit on this. Okay, when you push, right, as I told you before, the force from P and the force from the friction, it will create a moment, clockwise moment in this case. Okay, can you see my PPT on the tipping effect here, William?
Yes, sir.
Can you see my PPT here?
Yes.
Okay, so if you take a look here, P, if you push tall things like this, like a refrigerator or a tall box like that, okay, if you push it, okay, you give a pushing force there, there will be a friction force, there will be a weight of the things, there will be normal force, okay. When we take a look at that, okay, when you give a pushing force and it still stays stationary, okay, the friction force will be at the bottom. Okay, between the pushing force and the friction force, there will be a moment, clockwise moment in this case. Okay, and in order to stay stationary, yeah, the weight and the normal force is supposed to give a moment in the opposite direction of the moment from the P and F. Okay, so you can see, as you can see here, P and F will give a clockwise moment, W and N will give a counterclockwise moment. Okay, and the moment due to both is supposed to be the same. Okay, but there is a limit. Okay, there is a limit on the location of the concentrated normal force. Okay, as I told you, the concentrated normal force can only be placed between these 2 points, these 2 edges, the first edge here and the second edge here. So only can be the normal force can only be placed in between those 2 points. So in this area, it cannot be beyond those like this. It cannot. Okay, so the maximum that we can give is at the edge like this. Okay, when it is at the edge like this, the normal force is at the edge. It means that the condition is impending tipping. What does it mean? It means that tipping is about to happen. If you increase the pushing force, okay, tipping will happen. Okay, that is why if you push a refrigerator, or if you push your anything tall like that, yeah, or a table, or what else, your desktop computer like that. If the pushing force that you give is too high, okay, the height there is too high from the ground, there is a high possibility that the things that you push will tip over. It's because of that. Okay, the condition of impending tipping is the normal force is at one edge like this, one of the edge like this. It cannot be more than that. Okay, if it's already in this condition, impending tipping, and you increase the pushing force even more, or you increase the height of the pushing force even more, okay, it will tip over. That's the condition of tipping. So that's the idea of tipping. Okay, if it's the pushing force is not that high, or the height is not that high, right? Most of the time, the moment due to normal force NW with the moment of x there, it will be enough to counter the moment due to the pushing force and the friction. So as you can see there, P multiplied by H there, right? It's supposed to be a clockwise moment, and then we have a W multiplied by X. It's supposed to be counterclockwise moment. These two is supposed to be equal, always equal, like that. Okay. Normally, when we try to solve this, what we can do is we can create a sigma moment at this particular point, at the location of the normal force, concentrated normal force. Okay, in this case, you can see, right, P multiplied by H minus W multiplied by X is supposed to be equal to 0. Okay, most of the time it can be handled, but if X value is more than this, if your X value is more than this, it means that the normal force is outside of the edge. Okay, it means that it's already tip over. Okay, I will discuss about this even more next week after you try to handle your homework. Okay, please try to do your homework as best as you can. If you have a problem on that, next week we will discuss about it. Okay, I think that's all for today. Don't forget that wait a minute. Okay, I think that's all for today. Don't forget that next week, starting from next week, our class will be hybrid class, but I expect you to come to the class. Okay, if you are healthy, if you are not sick, if you don't get any COVID at that time, then come to the class. Okay, so you can learn better with me inside of the class. Okay, I think that's all for today. Thank you very much for listening. See you guys next week at 4104, 10 in the morning, Thursday next week. Okay, that's all for today. See you guys next week. Bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.
See you,
Thank
bye.
you, sir.